Okay, so welcome back. Today we are going to discuss problems in classical probability. So as we have seen in many examples, we have a situation where the number of elements in the sample space is finite, and because of the way in which the problem is stated, every outcome has the same probability. So we have seen already some examples. It's the case of the poker game, where every set of 5 cards is equally likely, is a possible outcome and is equally likely. And or the case of birthdays, where essentially every day is equally likely to be a possible birthday for every person. So in these cases, the probability of every outcome is constant, and then for any event, the probability of this event is just obtained by counting how many outcomes verify this event and divide by the total number of outcomes. Okay? So in the end, this is the realm of classical probability, and essentially computing probabilities amounts to a problem of counting. So it's important to recap a number of useful concepts for counting, which is essentially related to combinatorics. Okay, so the first one is the number of permutations. So if I have a certain number n objects, so the number of ways in which I can order these n objects is the number of permutations, and is given by n factorial, which is n times n minus 1 times n minus 2, etc. up to 2 and 1. Because, for the first object, there are n possible positions where I can put it in the list. For the second one, there are n minus 1. For the third one, there are n minus 2, etc., up to 1. Okay. So this is the factorial, n factorial, and there is an important approximation, which is called Stirling's approximation. That states that n factorial is asymptotically equal to the square root of 2 pi n times n to the n times e to the minus n. This is the leading behavior, and corrections to these results are of order 1 over n. Okay? So it is instructive to give you a derivation of this result, which is there is a derivation of this result in the book of Feller in chapter 2, which is a chapter that you are advised to study because it gives a recap of all the basic objects in classical probability and in combinatorics. So I will give a different derivation of this result, which is based on the identity that n factorial is actually given by the gamma function computed in n plus 1. Okay, the gamma function, so the gamma function is a function that is defined by this equation, so it's is a function that is defined on all the complex numbers z. It is a very interesting function, and so the reason why this is true is because you can, so when you write down gamma of n plus 1, this is the integral from 0 to infinity in dt t to the n e to the minus t. And now if you do integration by parts on this integral, what you find is that this is equal to n times gamma of n. And if you take n equal to 1 or n equal to 0, what you find is that gamma of 1 is equal to 1. Okay, so if you start from this equation and then iterate this relation that gamma of n plus 1 is n times gamma of n, then you immediately see that you get n factorial, okay, when you get to gamma of n plus 1. Okay, so how can we approximate this equation here? Well, the idea is that if you look at this integral, this function here, so it's a function that is falling off exponentially fast, but also that if n is large, this is, we are looking at large values of n. If n is large, then this function is also very small. So if I plot the integral, then what I will see is that this is a function that has this type of behavior with a maximum that I can compute from here, which is at t equal to n. Okay, this is a function t to the n e to the minus t. Okay, so then the idea is that this integral will receive its largest contribution around the region, from the region around its maximum. And so I can write t to the n e to the minus t as e to the minus, so first of all I want to make a change of variable so that the maximum is in a position which is independent of n. So I will write t as x divided by n, as n times x, so that as a function of x, this function here is a maximum at x equal to 1. Okay, and if I write it down, then this will be n to the n times x to the n e to the minus n times x. Okay. So then the next step is to realize that then this function n factorial can be written as n to the n times the integral between 0 and infinity in dx of e to the n times logarithm of x minus x. Okay? Now, when you find integrals of this type, there is a very general method to estimate it, which is called the Laplace method or the saddle point method. And it amounts to the observation that when n is very, very large, this integral receives its main contribution from the region where this function is maximal. Okay? And so the idea to compute this integral is to expand this function here around its maximum. So if I call f of x log of x minus x, then the first derivative is given by 1 over x minus 1. And so you see that the maximum is at x equal to 1, as stated before. And the second derivative is equal to minus 1 over x squared. So, etc., etc. So I can approximate this function close to the maximum as the function in 1. The function in 1 is equal to minus 1 times the first derivative times x minus 1, but the first derivative is equal to 0. And then the first term is essentially minus 1/2 the derivative, second derivative computed in 1, which is minus 1, times x minus 1 squared. And then there will be terms of order x minus 1 cubed. Okay, so the idea is to substitute this expression in this integral here. And so you see that you get n to the n e to the minus n, which comes from this minus 1 times n. And then you have the integral from 0 to infinity in dx of e to the minus n over 2 times x minus 1 squared. Then you have plus orders of n times x minus 1 cubed. Okay, so very good. So in order to perform to approximate this integral now, what we will do is another change of variable. We take a variable z, which is the square root of n times x minus 1. Sorry. Take z as being n times square root n times x minus 1. Okay? So if we do so, then this integral becomes n to the n e to the minus n. Now the change of variable gives me a factor 1 over square root n here. Sorry, I forgot a factor n when I did the change of variable here, because the dt is n times dx, so there is an n here, there is an n here. So there is an n divided by square root n. And then there is the integral z goes from minus square root n to infinity of dz e to the minus z squared over 2 plus orders of this term x minus 1 is order z divided by square root n. So n times x minus 1 cube is of order z cube divided by square root n. So you see that the correction, when n is very, very large, this correction will now be very small, and I can make a power expansion of these terms. So essentially I can write this as n to the n e to the minus n square root n times the integral. Now the integral here goes from minus square root n is large, so if I replace this minus square root n by minus infinity, this is going to imply an approximation which is exponential of order, an error which is of order e to the minus n, as you can check. So I can do this without problems. And then this is e to the minus z squared over 2 times 1 plus orders of z cube divided by square root n. Okay? Very good. So now if you want to compute the leading order of this integral, all you have to do is to compute the Gaussian integral, so this integral here, and I'm sure that you have already seen it, but let's do it once for all. So how do you do this integral? Well, it's an integral that you cannot do exactly. So what is easier to do is the integral of the square of this integral, because you can write it as an integral in dx on the whole plane of e to the minus x squared plus y squared over 2. And then I can change variable to polar coordinates, and I can write this as an integral from 0 to 2 pi in d theta, integral from 0 to infinity in r dr e to the minus r squared over 2. Okay, and here you see that you have r dr, which is exactly equal to d of r squared over 2. So this is the integral of dx e to the minus x from 0 to infinity, which is equal to 1, and this integral is equal to 2 pi. So the whole integral is just 2 pi. Okay? So the square of the Gaussian integral is 2 pi. So the integral is equal to square root of 2 pi, okay? So you see that you get exactly this formula, which is the square root 2 pi times square root n to the n e to the minus n, plus corrections. Now here I wrote correction of order 1 over n. Here there are corrections of order 1 over square root n. So it's an exercise for you to show that actually there is no correction of order 1 over square root n. The leading correction is of order 1 over n. Okay, so this exercise is important because the saddle point method, this type of method to estimate integrals of this type when n is large, is something that we will use over and over again in this course. Okay, so there are other important objects in combinatorics. The second one is just to remind you, so the number of ordered samples. So imagine that you have n objects, and each of these n distinct objects, say number 1 to n, and you want to understand how many samples of r different objects you can form from them. And this is called nr in the book of Feller, so we will follow its notation. And so the first object can be chosen in n ways, the second one can be chosen in n minus 1 ways, etc., etc. And the last one, the r object, can be chosen in n minus r plus 1 ways. Okay? So this is an object which comes frequently when you do sampling without replacement, when you are sampling from a system without replacement. And if you want to understand how many samples you can build, this is the number. Okay. We have already seen that this object appear in the problem of birthdays. So this is an important object. So the other objects, combinatorial object, which is very important, is the number of combinations. So it's the number of groups of R objects that you can form out of a set of n objects. So if you ask yourself, you have n objects, then you can ask yourself, in how many ways can I take, how many different groups of R objects can I build from this? And this is given by n divided by r, and it's just given by this number here divided by r factorial. And why do I divide by r factorial? Because I don't care about the order, the specific order. Here I was choosing the first, the second, and the last. If I don't care about, but the same group will be chosen in r factorial different ways when I change the order in which the objects are chosen. So this is the number of combinations of r objects from n objects. And there are two things that I want to remind you about this problem here, this object here. So this can also be written as n factorial divided by n minus r factorial. So this is also written as n factorial divided by r factorial n minus r factorial. Okay? So there are two properties that I want to remind you about. This is called the binomial coefficient, for reasons that we will see. And so the first one is that actually you can generalize this. You can use this expression. Actually, this expression here is valid not only for integer values of n, but for any real value of n. Because if n is real, this is a perfectly well-defined number. Okay, it's just the product of the number n times the number n minus 1, etc., up to n minus r plus 1. So this is an object which is well-defined for all real values of n, actually even for complex values of n, and integer r. Okay, and so is this object. So for example, we can write minus 1/2 choose k, and what will this be? Well, this is minus 1/2 minus 1/2 minus 1, etc., until minus 1/2 minus k plus 1. Okay, divided by k factorial. Okay, so this is a perfectly well-defined number. And interestingly, what you see is that I can manipulate a little bit this expression. I can take out a factor minus 1 to the k divided by 2 to the k, and then what I will have here in the numerator will be the product of 1 times this becomes 3 times etc., up to this becomes 2k minus 1 divided by k factorial. Okay, so this is the product of all odd integers up to 2k minus 1. It also has a name. This is called the double factorial with 2 marks. So, and of course, the product of all the integers up to 2k minus 1 is equal to the product of all integers up to 2k divided by the product of all even integers, which is again the double factorial. Okay, but the product of all even integers up to k is just 2 to the k times k factorial, right? So if I use this expression here, what I get is that this is equal to minus 1 to the k divided by 4 to the k times 2k factorial divided by k factorial squared, because there is this one and this one. Okay, and what is this? Well, this is minus 1 to the k divided by 4 to the k times the binomial coefficient of 2k choose k. Okay, so this is a very legitimate number. So this is also a very legitimate number, and the fact that we can use binomial coefficients for even for real or even negative values of n will be very useful, especially because of the second property I want to remind you, which is the binomial theorem. So the binomial states that for any two real numbers a and b and any real number n, you can write this as the sum from k equal to 0 to infinity of the binomial coefficient n choose k times a to the k, b to the n minus k. Okay, so usually you see this theorem with the sum being limited to n here. The reason why I'm extending this sum to infinity is because if you take this expression of nr, you see that when n is an integer and r is an integer, then this coefficient will actually be equal to 0 whenever n is less than r. Because if n is less than r, one of these factors will exactly be equal to 0, and then the whole product will be equal to 0. So it means that I can, if I generalize the definition of the combinatorial coefficient to general values of n and actually to real values of n, then the combinatorial coefficient will be equal to 0 if n is an integer, or is an integer, and n is less than r. Okay, so that it doesn't matter extending this sum to infinity, because all these coefficients are going to be 0 if n is an integer. Okay, so for example, now you see that with the equation that I wrote before, you can evaluate this sum So if you take this series, which looks apparently very complicated, however, this is nothing but, from what I wrote before, the sum from 0 to infinity of -1/2 choose k times z to the k. So this is nothing but 1 over the square root of 1 plus z. So this gives you an idea of why this generalization of the binomial theorem is important. Okay.